you very much for the nice introduction. I would just start right with our motivations. So nowadays, I think we, or most of you can agree that monitoring machines and using embedded sensors gives huge benefits in the terms of predictive maintenance and prolonging service intervals and all of the stuff. In this domain, we developed a sensor integrating M20 bolt, where we integrate a multi-axial force sensor. So you can see this down here. We have a standard M20 bolt. So for reference, it would be of this size, where we integrate a sensor, and on top of this are the electronics that we use to get the to control the sensor and to do the communication. A big constraint of this project was to maintain the outer dimensions of the standard machine element. That allows retrofitting, as you can just take out a regular bolt and put in the smart bolt. But this comes with the downside that we now have a very limited energy storage due to the fact that we have limited bolt volume, so we can only fit in a small battery. Also, due to this fact, wired connections are not an option. To make things even harder, we cannot guarantee for the availability of standard radio frequency connections or electromagnetic connections due to the metal environment such systems usually operate in. Also, there are very strict regulations on the power transmission or on the RF power that you can transmit. So in the terms of power, we cannot use this either. This is where the ultrasonic waves come into play, as they might provide a big benefit in this topic. We want to use them for communication and for power supply. And the good thing is that both of those have already been chosen to work in other domains by other groups. So using ultrasonic waves for data for communication is very well proven in medical applications. There you have implants that are powered or have their communication done through this ultrasonic waves. Also, in the metal environments, other groups have already proven this. They were even able to transmit images through an aluminum bar just using this sound. So we thought, can we use this for our application as well? And the goal of this work is now to use the ultrasonic power transfer first, or to elevate if it's possible. In our system, we have an asymmetric system, so we have one base station and one to many nodes. The base station is considered to be in a place that we don't have this tight constraints, so we have more bolt volume and we have a static power connection. So we can use this to put in the power, and then we have the nodes. In this case, it would be the sensors or the system integrated into the bolts. Now we want to characterize the influence of the thread, the clamping, and the alignment, as this has, to our knowledge, not been done by others in the terms of power transfer. For this, we decided to use a commercial transducer and attach it to a dummy bolt. We did this because transducer design, as you might know, is a whole a whole research topic on its own. We just wanted to rule out errors coming from this. So with this known transducer, we built up the setup. So we have a reference aluminum bar with 300 millimeters in length, where we attach two of those transducers. The one in blue down here will act as the transmitter, and the one in yellow will act as the receiver. And this is pretty much or pretty similar as a setup to other groups, so we use this as our reference. We now have we continued by connecting the transmitter to a waveform generator and performed current and voltage measurements, so we know how much energy went into this transducer. On the other side, we connected an oscilloscope with a 50 ohm termination, and again, with the voltage, we can now calculate how much power we received on the receiving side. Now we have two other setups that we used. So again, we have our reference, and then we have, with the same distance from transmitter to receiver, this setup where we have a bolt or screw that is put directly aligned to the transmitter into this aluminum bar. There we mount the same transducer on the back of this bolt here that you can see in green. So we have a directly aligned setup where the waves have to travel through this bolted connection. In the third setup, again, we have the same distance from transmitter to receiver, but now we use two aluminum bars that we clamp together in a clamped connection. So now we have not only the clamped connection, but we also have this 90-degree angle here that we have from the transmitter to the receiver. So we would expect that this, of course, performs the best and this the worst. We then continued by characterizing the transducers. And what we can clearly see, as we would also expect, is that for the transmitter, it was the same in all setups. We see the same characteristics. So we have clear resonance and anti-resonance. And for the other transducer that you can see up here with the different colors representing different mounting positions. And we don't see any influence of the mounting position on the impedance characteristics. Then we performed the first channel efficiency measurements where we use the direct coupling. So this is our baseline or our reference. And what we can see here is that we get a very, let's say, efficient channel of up to 4% at 2.2 and something megahertz. But what we can also see in this plot is that the channels are very narrow. So if we increase or decrease the frequency just a little bit due to the transducer settings and the overall structures, we will lose a lot of this efficiency. So we have to really hit this on the spot. We performed the same measurement with the other setups. And as you can see here now on the y-axis, this one, the reference, performed the best with up to minus 14 dBs of channel efficiency. With the directed aligned bolt in green, we still managed to get up to minus 39 dB of efficiency. And even if it's just minus 50 dB in channel efficiency for the bolted and 90-degree angle aligned bolt, it's still minus 50 dB. So there is still something. What you can see here, down here, is the ideal transmission frequency. That in the slide before, we had this narrow channels, and now we used every time the best frequency we found. And what we can see here is that they vary a little bit through the different mounting positions, which is probably based in the geometry and the reflections. Another thing we measured is the actually torque we used to mount those transducers. So there's, of course, if they are mounted too loose, the efficiency is worse than if they are mounted with more pressure. But as you can see here, for example, or here also very well, once you reach a required minimum, it doesn't increase much with the efficiency. We also performed a time domain analysis. We did this as a sanity check. So here in the zoomed in plot, you can clearly see the acoustic delay. So we did this to make sure that we actually measure the ultrasonic waves and not some coupled in radio frequencies or electromagnetic waves. What we can also see here on the outer scale where we have more time is that on the receiving one, we see in green here, we have oscillations. And those were also discovered by other groups before, was kind of expected. But we now confirmed that those oscillations also happen in these bolted connections, which of course is can cause problems if you try to transmit data. So yeah, just a really simple modulation scheme might not be enough, and this would have to be discussed further. So to conclude, we showed that ultrasonic power transfer is not only limited to directly coupled transducers, and that it can be a suitable option for bolted connections, and with this for sensors integrated in machine elements, as long as you have a metal environment, which you in a structure or a machine typically have. Of course, we have a significant channel loss, so this is everything but efficient. But as long as you have enough power on the transmitting side and the receiver or the sensor is energy efficient enough, this can be an option. The received energy is, in our case, sufficient to power the sensor module. So with the directly aligned bolted connection, we received 578 microwatts, while for this red one with the 90-degree angled clamped connection, we were still able to receive 140 microwatts. The next steps, we now plan to integrate this transducer into a bolt, and on this, my colleague will have a talk tomorrow, where he discusses how this can be integrated into the bolt itself. Also, we plan to evaluate different modulation schemes, so we also introduce the communication part into the system. The next step would then be to set up a demonstration platform that uses power transfer and data transfer for fully autonomous sensor platform. And with this, I would like to thank you for your attention, and I'm curious for your questions.